Okay, welcome to lecture here. We'll get started in just a second. So we're going to continue on lecturing on chapter 2. A reminder that you do need to have your video camera on as part of the class, so please put them on. Also, please put it here in the chat box for roll. All right, we'll get started here in just a second. Again, a reminder as well, the lecture notes can be found up there on our Canvas site if you want to use them and as we go through our lecture and stuff like that. And you hopefully should be able to see it on the screen. So a couple of things as we get going here. We finished up chapter 1. There really wasn't much going on in chapter 1, just a little bit about sort of scientific method and chemistry in general. So you don't have to worry really too much about that information there in chapter 1. Really, chapter 2 here is sort of the start of the real material, I guess, if you want to call it that. So in chapter 2 here, we're going to talk about measurements. We talk about calculations, significant figures. We're going to talk about dimensional analysis and all that good stuff, density as well. So a couple of things here, we'll get going. And again, if you're just coming in, a reminder, please put here in the chat box for roll. And again, if by some chance it's not your name there, make sure I can associate at least you're here with your correct name and all that good stuff. At this point, you're all muted. And again, if you do want to unmute yourself, you can to ask a question. A reminder though, again, if you do that, you will pop your video up as well, which should be on, which is perfectly fine. If you'd rather just chat me a question, you could do that as well. And probably should have my microphone in there so you could hear me as well. That would be good. So again, as I was saying, you can either unmute yourself if you like and ask a question as we go through, or again, if you'd rather not do it that way, you can definitely chat me one. And a reminder in terms of the chat as well, you can send a private message to me if you don't want everybody to see the question, or if you don't care, you could obviously send it to everybody as well. Yeah, so as we talked a little bit about last time, so the question was about, you know, kind of what you're going to be given in terms of the exam and stuff like that. It's going to be very minimal of anything. I guess I mentioned last time, they sort of cracked down a little bit on this class starting this semester and so forth. They want you to sort of have some knowledge of certain conversions, certain constants and those type of things. That's just sort of knowledge that you have. So when you continue on to Chem 1A, Chem 1B, you sort of know those things rather than always having to look it up. So as it stands now, pretty much you'll just be given a periodic table. As we go through it, there'll definitely be things on these slides that say you need to memorize and you need to know. So obviously those are things that you need to know and will not be provided for you. So again, in the past, they sort of give us some things, and starting sort of this semester, they are during the summer as well, they sort of really crack down on sort of the information given to you. So as of now, just a periodic table will be given to you, any type of conversions, constants that we come across. And again, I think a lot of them, they'll be highlighted in the notes, like you should know this. And again, those are things that you do need to know and stuff like that. All right. We will then start here and get going. Move a couple things out so I can actually see the screen. That would be good. All right, so chapter 2 is about measurements and calculations. So in terms of the procedure detail, I assume you're talking about the pre-lab. It's very simple in the sense of you just could do it many different ways, but the goal really of the pre-lab with the procedure is to sort of make sure that you've read the experiment before you get there, and obviously have an idea what should go on. So since you're not physically performing the experiment, we're just going to have you sort of copy the procedure in your own words. And that could be, you can use words to describe the procedures for every step that's in the experiment. You can do some type of flow chart if you want, where you kind of put arrows and boxes of sort of things that you do. But the goal really is for you to sort of have read the experiment before you get to the lab, hopefully have an understanding of physically what procedure-wise you would do. And in terms of sort of the format of it, it is kind of open-ended in that sense. Like I said, you can kind of do in words. Like I said, it doesn't have to be complete sentences or anything like that, but enough of detail, obviously, that we could understand what you were supposed to do physically when you did the experiment. Or again, you could kind of do more of a flow chart type of pattern where you kind of use arrows and maybe boxes of the steps and stuff like that. So again, you have a couple different ways that you could do that. But really the ultimate goal of that is just to make sure that obviously you've looked at the experiment, hopefully read the experiment, have an idea of what's going on. Other questions? Okay. And remember that that is due, well, right, about 10 minutes, I suppose. So hopefully you uploaded that. A reminder as well for the lab today, we are doing the second experiment, or the first real experiment there. And the pre-lab online is not going to be due until next week, to give everybody a chance to sort of get your OWL sort of in order and all that kind of stuff. But the written pre-lab is due today, though. So hopefully you got that up there.
Wait, so what was the pre-lab? Is that the lab activity we did?
Yeah, so the pre-lab is, again, basically there's two pre-labs that you have to do. One is the online pre-lab, and again, that's through the Cengage and all that. And that one for today's experiment is due next week on Monday. The second one that you have to do for every sort of real experiment that you would have a pre-lab for is to go and read the experiment and go through the procedure of the experiment and rewrite it in either your own words or do some type of flow chart of the procedure that you would have performed. And that should be uploaded on Canvas. There's like a little spot for each experiment that says pre-lab.
All right.
Other questions or anything? Okay. Perfect. Then let us roll with lecturing here. All right, so we're going to start with really scientific notation, and really in terms of measurements. Good, they should go back. Come here. There you go. So in terms of measurements, when we take a measurement, there really is sort of two parts to a measurement that's really important. And obviously the number part's important, but also the unit part. So for example, if I just wrote, hey, I have 100, that's a nice number, but we really don't have any relationship in terms of what that number means. I could have 100 pennies, which is very different than, say, have 100 candy bars. That's very different than having 100, $5 bills. So, the unit part is extremely important. It gives people a reference in terms of, what that number means, a relationship of, sort of what it means, what it is in relationship to. So whenever we do any type of measurement, and measurements are where sometimes referred to as being quantitative, quantitative usually is a measurement, and it should always have a number, and it should always have a unit part with it. So those two should always go together. For the most part, people get the number part, but always seem to forget to do the units. So the units are extremely important. They're also extremely important later on when we do some calculations that involve numbers and units. So you can see what units cancel out, which units don't cancel out. And a lot of times people kind of leave off the units, and it's not good because you don't know exactly what that number means. But also, when you do calculations like dimensional analysis, you can't really see the units canceling. So it's really, really important to make sure that you do include those units always in answers, also in calculations as well, so you can see the units canceling. Now, one way that we oftentimes will express numbers, and a lot of times in chemistry, we have very large numbers, we have very small numbers, and it's through a process that is known as scientific notation, which is a very common way that we do that. In general, scientific notation has a sort of a formula of n, 10 to the n. And n here is a number between 1 and 10. So not 10, not 20, not 30, but basically a number between 1 and 10. And times 10 to the little n is a either a positive or negative number, whole number, depending on really which way that you sort of move the decimal point to convert something into scientific notation. So for example, here we have this number here, which is a very large number. And the reason we do use scientific notation is at some point, if we're carrying all those zeros through those calculations, we're probably going to lose a zero somewhere along the way. So we do assume that perhaps a decimal would be here, even if it's not written. And to get this to a number between 1 and 10, we do need to go to the left. So that's 1, 2, 3, 4, 5, 6, and 7 places to get this number basically to a number between 1 and 10. And that's where the 9.3 comes from. Again, a number between 1 and 10, not 10 or above. And the times 10 to the 7 means we moved it 7 places. Now, in terms of this being positive, we don't have to put the positive, but it is positive. But if number is a large number, it will have a positive exponent there if it's large. And if it's a small number, it will have a negative exponent. So that's a good way to sort of remember it. Big number, positive, small number, negative, as you go through to write it. We'll talk why in a little bit here as well, why perhaps we dumped out all those zeros that are present and we just left it at 9.3. But to sort of give you a preview, the reason it has to do with significant figures. So that's why we ended up here with, I don't know why it's so spaced here on this name, but 9.3 times 10 to the 7 would be the correct way, again, to write that in scientific notation. Now, here again is a couple of other examples. This is 7.35 times 10 to the minus 4. This negative one means that it is a small number. And if we did need to go back into sort of decimal notation, what that would mean is we are basically going 4 places now to our left, because if we go 4 places to our left, it will make it a smaller number. So we're going to go 1, 2, 3, and 4 places to the left. We're going to put some zeros in there to do that. And usually we like to put that 0 in front of the decimal point, and this would be at 0.000735 is the same as 7.3 times 10 to the minus 4. So again, we move that decimal when the negative to the left. If it's positive, we go to the right. And I think that says 1.5 times 10 to the 6. So this is a positive exponent, which means it's going to be a larger number. So to make this number larger, we need to go to the right. And we would have 1.5, 1, 2, 3, 4, 5, and 6 places. And we would end up with 1, 2, and 6. Something that looks like so here. We'll talk about in just a second. This actually would not be correct in terms of significant figures, but that would be sort of the decimal form that it would come out to, non-decimal form. So negative number, smaller number, exponent, positive exponent, larger number. Now, when we do this, if a decimal point is moved to the left, as we just saw there, we can put it in scientific notation and it will be positive. Again, a larger number giving us that positive exponent. If we go to the right, we are making it a larger number. As you can see there, 345. Again here, we're assuming that the decimal is here. We would go 1 and 2 places over, and that is where the 2 comes from. And we get 3.45, which again is a number between 1 and 10. Here in decimal form, if we move the decimal to the right 1 and 2 places, that is where the 2 is from. Negative, again, a smaller number because we moved it to the right, giving us 6.71, which again is a number between 1 and 10. So again, it's very proper scientific notation. And where most people kind of mess up on is that front part. They sometimes use these really big numbers, you know, like 200 times 10 to the 4 or something like that. But properly written, it should always be that first number, a number between 1 and 10. So here's a couple of examples. Again, as we can see here, we're moving this 1, 2, 3, 4 places to the left. Again, it's a large number to begin with. And here we got our positive 4 and our 5.2. And here we're going 1, 2, 3, 4, 5 places to the right. Again, a smaller number we started with has that negative in there. All right. So I want you to take a second here and think about which one would be the correct way to express this in scientific notation. Let's see what we come up with. Okay, so we have 7882. Again, we would assume the decimal is here, so we're going to go 1, 2, and 3 places to the left. It was a big number, so that will give us 7.882 times 10 to the 3. And yes, I do see C. That looks good. C is the right answer there. Again, 4 places obviously would put us to the before the 7. And this is not a number between 1 and 10, this guy here. And this one also has negative number, which means we actually would be going the other way. And we'd have 0.007. So C would be the correct one here. All right. So looking at this one, take a second and see which one you think it will come up to. All right, so again, here we have a smaller number. So to get us to a number between 1 and 10, we have to go to the right. 1, 2, 3, 4, and 5 places, looks like. And in that particular case, that will give us 4.96 times 10 to the minus 5. Again here, minus because it started as a small number. We moved it to the right. So it looks like A would be the winner there as well. Any questions on how to write scientific notation? You do need to be able to obviously write proper scientific notation. You need to be able to take a number that's in scientific notation and convert it into a decimal and vice versa. Take a decimal and then convert it into something in scientific notation. All right, so this is obviously important ways, and as we'll talk about later, when we talk about significant figures, there can be sometimes only a way to get the right number of significant figures is to write a number in scientific notation. Now, more importantly, to be honest with you, other than sort of writing it, is most people don't know how to use their calculator and punch a number in scientific notation. So why don't we take a second here and actually talk about your calculator and how to properly enter a number in scientific notation. Most people are sometimes surprised to know that there is actually an exponent button on your calculator. And on most people's calculators, it will say like EE button. Some people's calculators will have like an EXP button. And some of the newer ones will actually have like a button like this, which if you have this button, and I'm kind of a newer calculator, I'll say sorry up front for you for that. And we'll talk about why that is here. But we'll first talk about these 2 buttons here, and then we'll talk about this button and some extra stuff that you have to do on it. So if we were to take a number such as this one that we have right here, and we wanted to actually put it into our calculator correctly, we would hit 4.96. Then you would actually hit the exponent button. And again, on a lot of people's calculators, they will have 4.96 and it'll pop up an E. On some people's calculators, it'll hit 4.96, maybe pop up a couple of zeros up on top. Then you want to hit actually your negative button, not your subtract button, which on most people's calculators look one of these two buttons. And then you would hit 5. And this would put a -5 here. This guy would change to a -5 at this point. Now, when you hit this E button, that represents the times 10 part of the number. And what that means is when you're putting it into your calculator, you should not be hitting the multiplication button. You should not be doing like shift log or anything like that. You should just hit that exponent button. And then again, if you needed it to be a negative exponent, you would hit that minus or negative button and then a 5. If it's a positive exponent, you would do the same thing. You just would obviously leave out, this part of it here, and you would have that. And you want to always punch things into scientific notation using your exponent button, because if you don't, what you will typically find is, especially when you're doing calculations, when you start multiplying things together, dividing things in scientific notation, you'll oftentimes find the front part of the number looks good, but that like times 10 part's off a little bit. And that's because you're probably not punching it in correctly. Now, before we do a couple examples, just to make sure everybody can punch it in correctly, if you happen to have this button and you don't have any of these other two buttons on your calculator, you could use it. The only difference is, in my experience, those calculators are programmed kind of weirdly, which means that you essentially have to put parentheses around all the numbers. So you would have to go 4.96, put the parentheses first, hit your exponent button, and then what it's going to do is actually put on your thing, I think, 4.96 times 10, and you'll have a number like up here, like a little box or something like that. And then you could do the -5, and then you have to hit the right arrow to bring it back down and close it off. So a lot of the newer calculators have this sort of button for the exponent, and they're kind of programmed, I don't want to say wrong, but not great. And if you really don't put parentheses around every individual number that you have, it will probably do the math wrong. So I want to say a lot of them used to have like kind of like a bluish white color. I want to say they're like Texas Instruments. I don't remember the number, but a lot of those kind of newer ones, they do have that button, and you do have to put parentheses around everything. Otherwise, you'll get it off. So why don't we try, let's go this way maybe. Whoops, wrong way. Go back, get something to write on. Let's do this. So why don't we just try some here? Let's do, take 7.85 times 10 to the -3 divided by, let's do 5.2 times 10 to the 12. See what you come up with. And then also do, we'll do 3.2 times 10 to the -4 times 4.56 times 10 to the 6. Let's see what you come up with here. So take a second, grab your calculator. I will as well, since I just made it up. Make sure we'll get to the same answer here. And again, make sure that you use your exponent button. You should not be using any multiplication buttons when you're typing the number in, just your exponent button. Okay, so let's take a look at the first one. So again, when you punch this into your calculator, you want to go 7.85. Again, you want to hit your exponent button. That represents the times 10 part. Since this is -3, you want to use your negative button. Again, not your subtract button. And 3, then you want to hit your divide button. and type the next one in, 5.2, exponent button, and 12 since it is positive. So in this particular case, if we do that, and again, if you do have the other button, you need to put parentheses around each of these numbers before you do it, divided by 5.2 to the 12. That is not right. Let's try it again with 7 point. Also punch it in correctly. That helps, I think. I just try that again. Divided by 5.2 to the 12. And it looks like we do end up with something like 1.5 times 10 to the minus 15 would be our answer. And again, if you got sorted the whole numbers like 1.509615, a whole bunch. Again, if you got the first number kind of right, but the exponent part is wrong, it is probably the way you're punching that into your calculator. So make sure that you do use those buttons. Let's take a look at the second one on the bottom. Again, we're going to follow the same approach, 3.2. We're going to hit our exponent button only, no multiplication button. And again, our negative, because it's a negative number exponent, and 4. We're then going to hit our multiplication button because we're multiplying, and going with 4.56, again, exponent button, and a 6 since it's positive. And if you do that one there, 3.2 exponent negative 4 times 4.56 exponent button 6 here. You get something like 1459.2, which obviously is not in scientific notation. And correct scientific notation, if we did, would make it something like 1.5 times 10 to the 1, 2, and 3. We give our answer there. Any questions on using your calculator, which I think honestly almost just as important as to how to properly write scientific notation, is where a lot of people really run into trouble, is when they're trying to use their calculator, is punching it in wrong. And most people do that mistake because they see the number times 10, so it does seem logical you should hit your multiplication button or something like that. But again, that's what that exponent button is for, is that times 10 part. So whenever you have a number in scientific notation and you're punching into your calculator, make sure that you do use that button, because you definitely will find yourself off. And you'll find yourself off even more later on when we start using things like logs, when we talk about pH and stuff like that, or inverse logs, you'll find yourself way, way off in terms of the number. Any questions?
Hey, I got a question. Yeah, so I got syntax error when I put it in my final answer.
For the first one?
Yeah.
And do you have an EE button?
Mine says just times 10 to the x. That's my button.
Times 10 to the x. Yeah, so you probably got to do parentheses around each of those numbers. And probably when you hit that times 10 to the x part, whoops. So you have something like that, yeah?
Yeah.
So usually when you do that on that type of calculator, again, you got to put that number, you hit that, it does put the times 10 out when you hit that button, right? And usually you're like up here. So you need to put the number in, and then there's like, you have a like arrow, like a circle with some arrows, right?
Yeah.
Yeah. So usually you need to hit that right arrow there, and I'll bring your parentheses down and big and not small. So if everything was like small up on top, it'll sometimes give it an error. So you got to do all those extra little things with that button to try it out, okay? Other questions or anything like that? Okay. So again, really important to make sure that you do put those things in correctly. Otherwise, you will find usually, again, the front part of the number is usually okay, but that back part is, the exponent part is usually not so correct. Now, in terms of scientific notation, a couple of other things. You want to make sure that you understand that obviously your calculator doesn't always give the answer in scientific notation or correct sig figs or anything like that. And, so keep that in mind as well. Also, in terms of scientific notation, for me personally in this class, and other instructors may be different as you go through maybe more chemistry classes and stuff like that. You don't necessarily have to use scientific notation and everything. As we'll talk about a little bit later on here today, sometimes you need to, because it's the only way to correctly give the answer. But if it doesn't say to use scientific notation, you don't have to use it in everything. If you want to, there's nothing wrong with doing it that way, but you don't have to necessarily always use scientific notation. Okay. So let's talk about measurements. Again, as we talked about, the unit part is really important. Again, it gives you that point of reference for what that number means. And so, for example, here we see 20 grams. So that tells you grams is a unit of mass. So we're talking about something that has to do with mass. 6.63 times 10 to the minus 34. And again, that actually should be an exponent here. So this number actually is a constant. It's 6.63 times 10 to the minus 34. And the units are joules times seconds. And this is actually a constant. This is what's known as Planck's constant, which is H. Planck's constant. We may see it in a later chapter come up, I think. But again, that should be an exponent, that minus 34. Just, I think PowerPoint made it a non-exponent there. And again, in terms of units as well, it helps us if we do have numbers, a way to sort of compare numbers, sort of understand, you know, the relationship of a number to another number. Obviously, if you're talking about something that's a mass and you're trying to compare it to something that's a volume, you know, they're not going to really compare apples to apples and stuff like that. Although if you have two measurements that are both masses, you then can obviously compare those guys pretty well since they are both masses. So here are some fundamental SI units, and SI, just so you know, is what is basically, in terms of units, there's really two sort of unit scales that, you know, sort of popularly been used over the years. There's basically the metric system, which is pretty much what everybody uses, except for us. Of course, we use the English system. So, you know, you could imagine as the world sort of got smaller, that's the sort of problematic if some people are using different units, say for mass, than other people are using, and it get really confusing. So believe it or not, in 1960, they actually had a whole convention about units. Probably was a lot of fun, I'm imagining, maybe. I doubt it. But in 1960, they basically came up with this idea of sort of a standardized system of units. And that's basically what the SI sort of refers to. Is actually the International System of Units, or this, I won't say it the French way, I suppose, but the right way probably. But the System of International Units is basically what the SI stands for. And it's really honestly based off of the metric system. So sort of the metric system, since everybody kind of uses the metric system, you know, except for us, for example, you know, it's really based off of the metric system. And so in chemistry and a lot of sciences, you oftentimes hear the SI unit. And again, that SI unit, again, is just that standard unit that everybody sort of agreed upon as a unit to use. So for example, if we're talking about something about mass, the standard unit is a kilogram. If we talk about length, we're talking about something like a meter. We're talking about time, the unit is a second. Temperature is a unit that you may not be so familiar with, but it's actually a unit known as Kelvin, named after a guy named Kelvin, obviously. It used to be called the absolute temperature scale. The amperage is an electrical unit of charge, and the amount of something is a mole. And those are some of the abbreviations over there. And much like the metric system in the SI system as well, we oftentimes, as you probably are familiar with, and we'll see in just a second, I think not too far down the road, we use prefixes, you know, to sort of change some of the meanings of it. So hence kilogram, kilo is 1,000, you know, centi is 100. So we have some of these prefixes that we do use with these sort of SI units, very similar to the metric system. So you should know sort of the basic SI unit for each of these quantities that are being measured. You know, the mass is a kilogram, the length is a meter, time is second, temperature is a Kelvin, the amount of something is a mole. We don't get into too much in terms of the amperage here in this class. Maybe in 1B, you get a little bit of it, but not a lot of that happens a lot in chemistry. But definitely the mass, the length, the time, the temperature, those are very common sort of units that we use a lot. And obviously, it doesn't necessarily mean that we always use these units. You know, For example, temperature is a very good example that for the most part, temperature we use either degrees Celsius or Fahrenheit. And then if we needed in Kelvin, we could do some type of conversion. And here are those prefixes. And these prefixes, whoops, come back. There you go. These prefixes do sort of change the meaning. So again, we use these a lot of times to help us not to have to write obviously so many zeros and so forth. So we have mega, kilo, deci, centi, milli, micro, nano. These are very common prefixes that we use, and I would say you probably should be familiar with these, what these are. Yeah, so probably for the most part, everybody on this list here, you probably should know. So these guys and the power to 10 notation. So let's take a moment here and actually talk about how to properly use this. This again is another area where a lot of people will mess up on in terms of not doing it correctly. So for example, when we say centi is 10 to the minus 2. And let's say that we had meters as our base unit, and we have centimeters, right? And a lot of times what people will do when they come to this table and go, oh, cool, centi is 10 to the minus 2. So that's 10 to the minus 2 centimeters in 1 meter. And that is not correct. It is actually the other way around. In one of the prefix unit, this is how much there are in the base unit. So it's very common people will get these guys sort of backward. Same thing with kilo is 10 to the 3. What that means is in say grams, in 1 kilogram, one of the prefix, there is 10 to the 3 grams. So this is our base unit, if you will, right? And this is our prefix unit. So when you use that 10 to the 3, the 10 to the minus 2 part, again, super common, people always get those backwards. So again, that's how much there is in the base unit to one of the prefix units. So when we talk about meters here, meters is our base unit. And this is one of the prefix units. So again, that is very much something that always goes backwards. By the way, when you do something like 10 to the minus 2, if you need to type that into your calculator, if you have the EE button, the EXP button, you probably could just hit it and go -2, or you could just type it in as 1 to the -2. And there's other ways we sometimes see these conversions. So for example, if you take 1 and divide it by 1 times 10 to the minus 2, what you actually get is another conversion that you sometimes see. So if we look at this guy, and we actually divide both sides by 1 times 10 to the minus 2, that gives us that there are 100 centimeters in 1 meter. So again, that is also another way that you sometimes see these guys when they kind of divide that to the other side. So again, how I got that, I divided the right-hand side and the left-hand side down here by 1 times 10 to the minus 2, and that gave me the other conversion that you may commonly either know or have seen before, that there's 100 centimeters in 1 meter. So sometimes see these prefixes sort of used a couple different ways. Sometimes people will use more of the whole number version, but a lot of times in chemistry, we use sort of this version of it as a conversion. And again, that's how much there is in a base unit to one of the prefix. And it doesn't matter the base unit. So if I did, for example, in 1 centiliter, there would be 10 to the minus 2 liters. So liter here, my base unit, centiliters, my prefix unit, is the same no matter what unit you go with. 1 centigram would be 10 to the minus 2 grams. So again, you could apply these to any sort of quantity unit, mass, length, whatever it may be. And it is basically the same conversion. But again, that's the major problem where a lot of people sort of mess up on, is that little step there. They always seem to want to do it like I originally wrote up here, sort of backwards, and don't do that. Yes. Otherwise, you'll be off for sure. So let's talk a little bit about length. Length, as we talked about just a second ago, for the most part here, length is a measurement usually are made a lot of times with a ruler. And as I mentioned before, really the two major sort of unit systems which helped us sort of develop the SI system is the English system, which again is typically what we use here in the US. And again, everybody else all around the world pretty much uses the metric system. So again, that's why we sort of, at least in science, developed the SI system, which is based off of that metric system. So English system here, we have yards, feet, inches, metric system, kilometers, meters, centimeters, millimeters are most common, centimeters and millimeters. And this conversion factor is one that you use a lot. And as you can see here, also something that you do need to know by heart, and that is 1 inch is 2.54 centimeters exactly. And that brings us to a ruler, which sometimes people don't really know how to read, right? So top part on a ruler is our inches, bottom part is our centimeters, and if you look, a little hard to see here maybe on my screen, but maybe not on yours, all the little dashes are actually millimeters. Yeah. So the little markings on the bottom of the ruler where the centimeters are the millimeters, and the big guys are the centimeters, and on the top is an inch. And you can see here, 1 inch is exactly 2.54 centimeters as you read it. All right. Now, volume is the amount of three-dimensional space that's occupied by a substance. And a couple of things about volume. A very common unit of volume is a milliliter and a liter. Now, milliliters and liters are very common units of volume. Now, another very common unit of volume that we come across a lot is a cubic centimeter. And a cubic centimeter also sometimes the same as a cc, which stands for cubic centimeters. And that is also equal to a milliliter. They're all basically the same. So 1 milliliter is the same as a cubic centimeter. cc, you sometimes hear like on TV shows, medical shows, right? Give the guy 5 cc's of this, 4 cc's of that. So you're basically talking about a milliliter. So in England, I think they use cc a lot. I had a girl from, I think, the United Kingdom, and she would say cc all the time. I'm like, okay, that is cubic centimeters. How do we get something like cubic centimeters? Well, cubic centimeters are basically one way you could get a volume is to take length times width times height. Now, if these are each measured in centimeters, which is a length measurement, you take centimeters times centimeters times centimeters, you get a cubic centimeter, which is a volume. So one way you could kind of get a volume of something that's sort of like a cube is you take the length times the width times the height, or the thickness in one of those instead. And again, individually, they're length measurements. So if you took the measurement for the length in centimeters, that is a length measurement. You take the measurement of the width in centimeters, that also is a length measurement. And if you take the height or thickness there in centimeters, that is also a measurement of length. But when you multiply all these guys together, you then end up with your cubic centimeters, which is a volume. So again, individually, each of those measurements of the length, the width, the height, they're individually a length measurement, but when we multiply those guys together, it becomes a volume. Also, you should memorize this, right? 1 milliliter is the same as a cubic centimeter. So again, make sure that you know that. So talking about a centimeter, either been a meter by itself, we're talking about length, we're talking about any of those length measurements that have been cubed, they become a volume. So meters cubed is a volume, decimeters cubed is a volume. As you can see up here, 1 decimeter cubed is the same as a liter. So again, that's a very common way that we do get volume in chemistry, and it does come out a lot, especially in the context of density. We see it a lot, cubic centimeters. It's a very common unit of density. Now, mass measures the amount of matter that is present in an object. And now there is a difference, between mass and weight. So mass is independent of gravity, while weight of something takes into effect gravity, or the force of gravity. So mass is sort of independent of the force of gravity, while when we talk about the weight of something, it is dependent on the force of gravity. So if we take the mass of an object here and say the mass of an object on the moon, they will have sort of the same mass. If we take the weight of an object here and the weight of an object on the moon, it will have a different weight because there's a different force of gravity associated with it. So when in chemistry and pretty much most sciences, we call this process mass. You really shouldn't call it weight. Yeah? So if you go to weigh something, which is oftentimes what confuses people, right? The process of actually getting a mass is the process known as weighing. But when you do that, you should refer to it as the mass. Again, it takes out sort of the force of gravity associated with it. So it's basically the measure of the amount of matter that's present in an object. And again, some common English system, common metric system. Pounds we use a lot here in the English system. Kilograms, grams, and milligrams are very common. Like even at the doctor's office, they oftentimes will weigh you in kilograms rather than pounds. So that's a very common sort of conversion that's used. And a conversion again here that you should know and memorize as well is this one here. And that is one that you use a lot throughout chemistry. 1 pound is 453.6 grams exactly. And again, that is a conversion that you definitely should know by heart. And again, as I mentioned at the start here, they have sort of cracked down and want you to really sort of know these things, not only for this class, but again, as you continue on to Chem 1A and Chem 1B as well.
Question.
Yeah.
What's it say at the top right? What does that say?
The force of gravity. Weight takes into account the force of gravity.
Okay, thank you.
Other questions on that? Okay, so let's take a look here. For each of the following, take a second here and figure out, is it mass, length, or volume we're talking about here? And then we'll talk about it here in just a sec. Okay, so let's take a look here. So we got a bag of tomatoes is 4.5 kilograms. So again, kilograms, right, is our mass. Person is 2.0 meters. So meters is a unit of length. Here we have 0.50 grams. So grams again is a unit of mass. And a bottle contains 1.5 liters. So liters is a unit of volume, right? So again, these are common units that we come across for these quantities of measurements that we commonly make. So let's talk about also another important sort of aspect of measurements And that has a lot to do with two things that are oftentimes used sort of interchangeably, but they actually do mean different things. So for example, when we talk about accuracy, accuracy is basically how close your measurement is to the true value of the measurement, the correct value of it. While when we talk about precision, it means how much does a group of measurements agree with each other. So how reproducible are sort of your results. So the classic here is you're throwing darts at a dartboard. So for example, here we throw the darts, we're all over the place, right? When you shoot a dartboard, you're looking for bullseye in the middle. So none of these shots really are accurate. They're not near really what we're shooting for, which is the middle. And we also see they're not very precise either because they're kind of all over the place. This poor guy missed the board completely there. So, you know, he goes double or nothing. We'll try it again. Throws the darts. And now we see we have a sort of a clustering of all these darts, which means it is very precise because they're all near each other. They all sort of agree with each other, but it's not very accurate. Again, pretty much all of them are pretty far away from the actual true value or the bullseye that we're shooting for. So he goes triple or nothing, right? He shoots them all, and they all pretty much all hit kind of dead center there, bullseye, and which means A, they're accurate because they hit pretty close to the true value there that we're looking for, and they're all pretty much dead on there as well. So you can see a couple of things here. You know, if you're accurate, you probably will be pretty precise, and you could be very precise like over here and not so accurate at all. So that what that means is, for example, you could do something consistently the same, but it could be wrong every time you do it the exact same way, and you end up with the exact same answer, and you're very precise, but not very accurate. So accuracy, again, how close we are to the real value, the true value. Precision, how close a set of numbers are to each other. And we oftentimes will use precision to help us indicate something like how reproducible something is, how many trials. So oftentimes we do multiple trials to understand, you know, how reproducible an experiment can be. Now, obviously, when we take measurements, we want to be both accurate and precise, kind of like the last guy on the right there. And again, usually if you have pretty good accuracy, you're probably going to be pretty precise as well. So here, when we reflect on the reproducibility of a given type of measurement, here that we are referring to reproducibility. That is the precision. So again, precision is how close a set of numbers are to each other. So that would imply how many times you kind of redo it and end up with the same answer. While when we're looking for agreement to the true value, that is what we're looking at accuracy here. So again, if you're very accurate, that means you hit a number that's very close to what the actual number definitely should be. Any questions on the difference between accuracy and precision? And again, if you have questions, feel free to ask them. Now, let's talk about actual measurements and what happens when we do take a measurement. Now, any type of measurement that we take, there's always going to be some degree of uncertainty associated with that measurement. There's always going to be some degree of, I'm not really sure what that number is. And when we record a measurement, it's always important to record all the certain digits first and that first uncertain digit. That is actually what is referred to as significant figures, as we'll talk about. So significant figures is when you take a measurement and you record all the certain numbers plus that first uncertain number. So what do we mean? So for example, we'll see maybe a better picture in just a sec. Let's say we had we'll say this is 2, this is 1 over here, and we'll call these centimeters. So let's say we had a ruler that looked something like this. And let's say we had an arrow that looks something, we'll go-ish there. Now, when we look at this, we want to look at how many small markings there are between the two big numbers. So the big number here is 1, next big number is 2. In between, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So there are 10 markings, little markings, between 1 and 2. That means that each marking represents, in this case, 0.1 centimeters. This first mark here would be 1.1, 1.2, 1.3 as we continue down the path here. I'll kind of go on an angle since I didn't write it very big. Now, when we look at this little kind of arrow or thing that I made here, no matter who looks at this scale, everybody should agree it is at least 1.1, 1.2, 1.3, 1.4. It's not exactly at 1.5 marking, but anybody that looks at it should go, it is at least 1.4. Those are what we refer to as the certain digits when we take a measurement. Again, no matter who takes a peek at that scale, everybody should agree. Now, when we look at it, we see it is not exactly at 1.4, it's not exactly at 1.5. So that is where the estimate comes into play. I may look at it and go, I think it's dead center between those two, and I'm going to call it a 5 centimeters. Now, somebody else may look at it and go, I think you're crazy. This is clearly way closer to the 1.5 marking. I think it's like 1.49 or something like that, maybe, centimeters. And that is where our uncertainty lies, is in this last digit here. And when we would make a measurement like this, so for example, I would take 1.45 centimeters, we would record all the certain numbers, which are these two. And our first uncertain number. And that is what we should record. And this would also tell us how many significant figures this number has. And in this case, if you look at it, 1.45 would have 3 significant figures. Again, the significant figures is all the certain numbers in a measurement plus that first uncertain number. Now, if we look at sort of we'll have maybe a better picture in a second here, but just do my bad picture to begin with here. We'll go with 10. Actually, yeah, let's see. Maybe I got a better spot here. Perfect. We'll borrow this so I can actually draw it here. Let's draw this better. All right, let's go with 10. And 20. And what we'll do is kind of just put the scale to the right so we can kind of see it. All right, you can imagine that's equally distanced and not very badly drawn like I just did there, but we'll call these milliliters. And for example, this is 10 milliliters, that's 20 milliliters. In between the 10 and the 20 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings, again, between the 10 and 20 milliliters. That means in this particular case, each of the smallest markings is actually 1 milliliter. This would be 11, right? This would be 12. This would be 13, 14, 15, 16, 17, 18, 19, and so forth. So if we had a liquid, and by the way, when we take a measurement of a liquid, we usually will see a curvature of the liquid. And that curvature of the liquid is what is known as the meniscus. And we always read at the bottom of the meniscus. And sometimes it's easier to see, and sometimes it's a little harder to see. So for example, I'm just gonna, again, very badly draw this here. We'll go right about here. We'll call that the meniscus. So again, when we would make the measurements here, everybody that looks at it should agree it is at least 15. Those would be our certain numbers. But in this case, again, not exactly at 15, not exactly at 16. So again, I may look at it and go, I think it's 15.2 milliliters. Again, this would be my first uncertain number. This also then would have my two certain numbers, my first uncertain number, three significant figures as well when we take this reading. And it's really important when you look at the scale to try to figure out, how far you could take the reading. And as we will see in just a second, typically you could take the reading to one more place to the right of the smallest marking. So for example, here, the smallest marking is 1 milliliter. We were able to go to the first decimal place, one more place to the right. In the example that I did over here, the smallest marking was the first decimal place. We were able to take the reading to the second decimal place, one more place to the right. Not 100% of the time can you do that. And then that's why it's really important to always look at the scale. So for example, let's take our same kind of scale here and go 10, 20. Same really badly drawn graduated cylinder here. And we do a little volume right about there. Now when we look at this scale here, that's 10, that's 20. There's now only 1, 2, 3, 4, 5 markings between 10 and 20. That means each of the smallest markings in this particular case is now 2 milliliters. That would make this 12 milliliters, 14, 16, 18 milliliters. Now when I look at it, I am actually between 14 and 16. Between 14 and 16 in this scale, the best thing you could do is call it 15 milliliters. That's because there's not enough room in here to make basically the 10 dashes for the 15 and the 10 dashes for the 14. There's not enough room to do that. So again, it really does depend on the scale that you're looking at as to how far you can take the reading. Now take a second here. This would then have how many significant figures? Hopefully when you look at this number, you would then know it has actually 2 significant figures, this number. And that means that the uncertain number here is actually the 5 in this particular case. It's the uncertain number. The 1 here is the certain number. In this particular case, it could be as big as 16, could be as small as 14, it could be somewhere in that region, and that's where the uncertainty lies. So it's always really important when you kind of look at a measurement or you go to take a measurement, it's important to look at the actual device that you're using, the piece of equipment, and figure out what is the farthest that you could actually take that reading to. And again, it usually involves, in most cases, going one more place to the right of the smallest marking. Questions on that there, as I think I jumped a few slides, but we'll cut to it here. So if we look at these numbers here on the bottom, 1.34, it has a precision to the 100th place, and that's where the uncertain digit is. So when we see a measurement given to us as 1.34, these first 2 numbers here would be our certain digit. This would be our uncertain digit, and this guy would have 3 significant figures in that case. 23.004 has the precision in the thousandths place. And what that would tell us is, in this particular case, all 4 of those numbers are a certain number, and our uncertain number is right here at the end. And in this particular case, that would give it 1, 2, 3, 4, 5 significant figures in that particular case. Yeah, so the question is, do you take, typically when you're recording an actual measurement, you do only take the first uncertain number, because your measurement is only as good as your worst measurement, and that place where you first get that uncertainty happening is as good as a measurement you're going to actually get, because that's basically where the error in terms of precision lies, is in that first uncertain digit. So always the all the certain numbers and then only the first uncertain number. And again, that's typically what we take for our measurements, and that is what gives us pretty much our significant figures. Other questions on that? So here's sort of what we just kind of went over with my pictures, but again, a more mathematical approach to sort of figure it out here. To determine the uncertainty, you take the smallest guy and basically divide it by 2. So for example, in the one where we did the smallest marking was 1 milliliter, we divided by 2, got us the 0.5, and that is the precision that we'd have here. So if it's like 1 centimeter is the smallest marking divided by 2, the precision there would be plus or minus 0.5 centimeters in that particular case. If the smallest marking was 0.1 and divided by 2, that's how we get to our hundredths place there at 0.05 in terms of the precision. And again, if you did have a ruler, every number that you record here that had this sort of setup should always end up at that place. If your ruler was able to go to the 0.1, you should go there. And again, you can see pretty much it is one more place to the right of the smallest marking as to where you can kind of take that measurement. So here's just some of those things that we talked about. Determine the unit of the instrument is really important when you're taking a measurement and trying to figure out the uncertainty. Again, the thing you really want to do is look at it and figure out what does each of the smallest markings represent. And then you can determine the uncertainty by basically dividing the smallest marking by 2. And again, that will give you that, like we just saw there, plus or minus 0.5, plus or minus 0.05 in terms of the precision. And again, always record all the certain numbers plus that first uncertain number. And again, pretty much that is what significant figures are. So here's again another example here. If we look at this scale here, again, this is our 2 and our 3 in terms of our centimeters. And if you count up all the little markings, and by the way we typically count, sometimes people are not sure. We don't really start counting at the first number. We kind of go here and start counting. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and end at the next big number. So that's how we get our 10 markings. We don't include obviously this one here. And as we saw before, since there are 10 markings between basically 1 centimeter, each of these are 0.1 centimeters, which means on this particular measurement, you should be able to go, to the second decimal place here. So if we zoom it in here, again, it's close to 3, but not exactly 3. So they recorded somewhere between 2.8 and 2.9. And as they follow through the precision here, they determined that we can divide that to give us our 0.1 and divide it by 2, which will give us our uncertainty of 0.05 like we've been talking about. And we can now record it. Again, these are our certain numbers. Again, no matter who takes a peek at it, everybody should agree that it is at least 2.8. And now this is where our estimate comes into place. Again, this is a super zoom of that little space between the tip of it. And again, in their particular thing, they feel it comes about halfway there between the two numbers. And they record 5, which would be our first uncertain number. So this would also have 3 significant figures. Any questions on that? And again, somebody may look at it and go, I think it's a little bit closer, may record 6, may record 4. Usually when we think about the last digit, the uncertain digit, we usually think it could be as big as plus or minus 1 of that last digit usually in terms of sort of the uncertainty that occurs. All right, so take a second here and figure out what you think the reading here would be. Okay, so let's take a look. So again here, this is 2, this is 3. That's sort of our big numbers. So our small numbers starting to count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings. So again, there's 10 markings between basically 1 centimeter, which means that each of those markings basically are, again, 0.1 centimeters. So this first guy here where my arrow is would be 2.1, 2.2, 3, 4, 5, 6, 7, 8, 2.9, and then 3. So again, no matter who looks at it, everybody should agree is at least 2.5. It's at least 2.6. And again, those should be your certain numbers. Again, we see it's not exactly at the 2.6, and perhaps you may look at it and say it's not exactly at the 2.7. So here's where our estimate may come into play. And again, we should be able to go to one more place based on the numbers that are there. If we divide it by 2, 0.05, right? And we should be able to hand out to the second place, which automatically should eliminate this guy, should eliminate that guy. That is too many. And then that leaves us pretty much these guys here. So again, it's very close to the 2.7, so perhaps 2.69 would be good, which should eliminate that because 2.5 is way back over here. Now we have these two here. Now in terms of our precision, as I just did up here, it should go to the 0.05, which means D should be the right one. If we had this precision, that means that technically this number should be like 2.690 or something like that. We could go out to that place, so we don't have that precision either. So it should be D here. Any questions on
Yeah, I got one.
Yeah.
So where do you get the 0.1 from that you're
Uh,
dividing from?
Yeah, so the 0.1 represents how much each of the little markings represent.
Okay.
So again, we started here at 2. So that first little marking would technically be 2.1. The next one would be 2.2, 2.3. And that's what each of the little markings represent, right? Because if we keep going all the way through, this would be 2.5, 2.6, 2.7, 2.8, 2.9, and then 3. Yeah. So each of those little markings represents 0.1 of a centimeter. And again, to get the precision, we could divide it by 2 to get the technically how far we could take it, but usually you could, in most cases, go one more place to the right of that whole number.
Okay, thank you.
Yep. Other questions on that? All right, why don't we try one more here before we wrap it up? Take a reading on that one. Okay, so since we're getting in here, let's take a look. So again, we're sort of right around here at the 9. So we could kind of look at the 9 to the 10. And again, if we count starting with the mark next to the big number, so that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings. Again, we have those 10 markings between basically 1 centimeter difference. And again, each one would then be 0.1 centimeters. So again, the first marking after the 9 is 9.1. 9.2, 9.3, 9.4, 9.5, and so forth. So we want to take a look at it here. It's definitely past the 9, so everybody should agree to the 9. Now, again, because of this, we can divide the smallest marking by 2 and get that 0.05 centimeters of the precision. Also tells us we could go to the second decimal place when we make this reading here. And in this case, that means it's definitely not going to be this guy because it's not the second decimal place. Shouldn't be that guy either. This guy's the third decimal place. So it does has to be this one here. So it's at least 9.02 as it's just past the 9. It's definitely before the 9.1, so it's definitely not 9.1 in centimeters with our precision of 0.05 centimeters there, plus or minus. Any questions on that one? 9.005 is too far on this scale. You don't have the ability to do that. Again, in order to have the ability to do that, each of the smallest markings would have to be something like that. But since the smallest markings are only to our 10th place, you don't have the ability to go that far. This is not enough, and that is not enough either. So why is, for example, this not enough, right? Just to finish up here. If we took this measurement here, this guy would have 2 significant figures, which means the uncertainty would be here. This could be something like 9.1, 8.9, which is a pretty big span as to what we're looking at. Here, the uncertainty has 3 significant figures, which means this could be something like 9.03, or it may be 9.01, you know, plus or minus there. And that is more likely what the measurement is here than saying it could be as big as over here or as small as over here. So there's a lot more error involved in that. And that's why it's important to make sure you don't cut off significant figures and you take the measurements to the right numbers. Otherwise, you're really making your measurement a lot worse. All right, we will stop here for now for lecture. We will go off to lab in about 15 minutes or so. We went a little bit over, so we'll start right there around 12-ish. We're going to do experiment 2, which is basically more measurements. I think what we're going to do is we're going to do a little bit more lecturing on this. We have a few more slides that will help us with the lab, and then we'll do the lab, and we'll talk about when everything will be due. So otherwise, make sure you put here, if you haven't done so, in the chat for the roll, and I'll see everybody in about 15 minutes. Go through the lab link, though.